In level 77 of ChemChallenge, the task is to synthesize formaldehyde and hydrogen from methanol. The reaction equation is complete and balanced. At 298 Kelvin, this is an endothermic reaction. The enthalpy change, delta H, is plus 124 kilojoules. In this reaction, 2 moles of gas are formed from 1 mole of liquid. Therefore, the chemical system becomes more random when methanol rearranges into formaldehyde and hydrogen gas. The change of entropy in this process, delta S, is plus 222 joules per Kelvin. The combination of delta H and delta S at 298 Kelvin gives a Gibbs free energy change of plus 57 kilojoules. This means that at 298 Kelvin, the conversion of methanol into formaldehyde and hydrogen is non-spontaneous. It also means that the backward reaction, hydrogenation of formaldehyde, is spontaneous. Given the positive delta S value, the forward reaction becomes spontaneous at temperatures greater than 556 Kelvin. Therefore, increasing the temperature of this reaction is an effective approach to solving level 77. There is, however, another way to make this reaction spontaneous. The reaction might proceed even at 298 Kelvin by employing photochemistry. Photochemistry uses electromagnetic radiation in the ultraviolet visible range of the spectrum to drive chemical reactions. 1 mole of photons with specific wavelengths denoted by lambda carries an amount of energy, E, which is calculated using the Planck-Einstein relation. For example, 1 mole of 180 nanometers photons carries 664 kilojoules of energy. Overall, the shorter the wavelength, the more energetic the photons are. To explain how photochemistry can turn an endothermic reaction into an exothermic one, it is convenient to consider photons as reactants. However, unlike actual chemical substances, which chemists can weigh and add to a flask before the reaction, photons must be supplied continuously. In practice, this is done by illuminating a photoreactor with photons of specific wavelengths that are absorbed by reactants. Ultraviolet visible absorption spectroscopy is used to identify photons' wavelength in the electromagnetic spectrum that are absorbed by a specific substance. The human eye is a sensitive spectrometer by itself. We perceive colors as a response of our eyes to interaction with photons having wavelengths in the range 400 to 750 nanometers. The opposite statement is also true. From the color of a substance, we can estimate the wavelength of photons that the substance absorbs. For example, substances that appear as colorless liquids or white solids, such as titanium dioxide, absorb photons with wavelengths shorter than 400 nanometers. It is outside the spectral range of the human eye. Substances that appear as yellow liquids and solids, such as elemental sulfur, absorb photons with wavelengths of approximately 460 nanometers and shorter. Orange substances such as cadmium sulfide absorb photons with wavelengths of approximately 590 nanometers and shorter. Methanol is a colorless, transparent liquid. It absorbs photons with wavelengths shorter than 200 nanometers. Calculations on the photochemical conversion of methanol to formaldehyde and hydrogen driven by 180 nanometer photons indicate that the reaction is spontaneous at 298 Kelvin. A graphical illustration of these thermochemical calculations is shown in the following diagram. Recall that the standard enthalpies of formation of elements in their standard states are 0. When 2 moles of H2 gas, half a mole of O2 gas, and 1 mole of carbon atoms in the form of graphite combine to form 1 mole of liquid methanol, at 298 Kelvin, 240 kilojoules of energy are released. This energy corresponds to the standard enthalpy of formation of methanol in a liquid state. Similarly, when 1 mole of H2 gas, half a mole of O2 gas, and 1 mole of carbon atoms in the form of graphite combine to form 1 mole of gaseous formaldehyde at 298 Kelvin, 116 kilojoules of energy are released. This energy corresponds to the standard enthalpy of formation of gaseous formaldehyde. Therefore, from a thermodynamic perspective, formaldehyde is approximately 124 kilojoules less stable than methanol. Photochemistry can enable a chemical system to transition from a thermodynamically more stable state to a less stable state via an electronically excited state. the absorption of 1 mole of 180 nanometer photons by 1 mole of methanol molecules formally produces species that are 664 kilojoules less stable than methanol in its ground state. The transition of the chemical system from this excited state to a state composed of formaldehyde and hydrogen is spontaneous. Therefore, in level 77 of ChemChallenge, the task can be solved by using a light-emitting diode that supplies 180 nanometer photons to methanol. In the real photochemical experiment, the absorption of photons of a specific wavelength by methanol does not guarantee its effective conversion into formaldehyde and hydrogen. Absorption of photons by a reactant is necessary but not sufficient for the reaction to proceed. In practice, methanol is converted into formaldehyde and hydrogen by employing a photocatalyst, a substance that absorbs photons and drives the target reaction without being consumed itself. One of the advantages of a photocatalytic approach compared to a purely photochemical one is that a photocatalyst can utilize photons with longer wavelengths to drive the reaction. Especially appealing is using natural solar light, the most sustainable source of energy. In this video, a photocatalyst immobilized on a solid surface drives the conversion of ethanol into acetaldehyde and hydrogen using natural solar light. Visit savateevgroup.com and get your copy of the game and other educational materials.